Today, let's break a misconception. Can air conduct electricity? We have always read that air is a bad conductor. Let's take a copper wire and make a coil with it.
We connect the two terminals of this coil to the multimeter. Now, let's take this setup near a high voltage line.
Remember, no need to climb the tower. You will notice that the multimeter is showing a voltage reading.
This simply means this energy is traveling through the air to the ground. In other words, wireless electricity transmission is happening. So, in this situation, we can say that, when the voltage is very high, air can act like a conductor.
So can we also say that in these UHV lines, the conductors of the three phases are kept far apart from each other?
And we rely on the air between them to act as an insulator. But we just saw that air can also conduct electricity, especially when the voltage is very high. This is why substations are built over a large area, so the air between one phase and another can act as an insulator. This type of switchyard is called an Air Insulated Switchyard, or AIS.
But we can build this same 440 kilovolt switchyard inside a small building.
The only difference is that instead of air, we must use gas insulation. This is called a Gas Insulated Switchyard, or GIS.
The incoming line first has a lightning arrestor, which protects the system from overvoltage surges.
Next is the CVTT, which is used to measure the high voltage.
This wave trap blocks the high-frequency communication signals that travel on the power line. This is the bushing. It connects the open-air conductor to the gas-insulated system. To hold this conductor in the middle of the pipe, epoxy resin spacers are used. The spacer mechanically holds the conductor and electrically isolates it from the pipe, preventing short-circuiting with the outer casing. Another type of spacer is the barrier spacer. It completely seals off a chamber. Compartment. Each of these compartments is filled with sulfur hexafluoride, or SF6 gas, which is a much better insulator than air.
In a normal high-voltage line, an electric field is generated in the air around the conductor.
But SF6 gas has a dielectric strength of about 89 kilovolts per centimeter, which is almost 3 times higher than air.
This metallic enclosure works on the Faraday Cage principle. Animation shows the induced current flowing safely to the ground via the earthing wire, making the outer pipe safe to touch. Therefore, this is the line earthing switch. It grounds the line during maintenance. This is the isolator or offload switch. It is used to disconnect the circuit when there is no load. For safety, after opening, a part of the isolator connects to the ground. This is the current transformer, or CT. The main conductor acts as the primary winding. This is the circuit breaker. It can connect or disconnect the line even under full load.
At that exact moment, a high-pressure blast of SF6 gas is forced onto the arc, which instantly extinguishes it.
After the arc is quenched, the contacts are fully separated and the flow of electricity is safely stopped. A substation usually has two main bus bars, main bus 1 and main bus 2, for reliability. From the bus bar, the feeder lines utilize these isolators and the circuit breaker to transmit power throughout the network. Often, line A will feed bus 1 and line B will feed bus 2, and the two systems run independently. But what if one of the incoming lines fails? This is where the bus coupler comes in. The bus coupler is basically an extra circuit breaker that can connect the two main buses together. In this way, a GIS substation manages power reliably and safely, using very little space.
It takes up to 10 times less space than an air insulated substation.
To keep learning through animation and visualization, please subscribe.